Go ahead.
So our third talk would be by Jonghyeon, who will tell us about S1-Equivariant, relative symplectic cohomology, and relative symplectic capacities. Go ahead.
Okay, thank you very much for the opportunity to give a talk here. I will talk about S1-Equivariant relative symplectic cohomology, and as an application, I will talk about relative symplectic capacities. And here are some notations and terminologies that I am going to use throughout this presentation. And the Novikov field is defined by the set of formal power series where the coefficients are rationals and the exponent of the formal variables are real numbers and the limit of the exponent is infinity. And this Novikov field always comes with a valuation map. And valuation of a non-zero element is given by the minimal exponent whose coefficient is non-zero, and the valuation of the zero element is defined to be the infinity. And for each r, real number r, we can define lambda greater than or equal to r by the pre-image of the infinite interval r to infinity under the valuation map. And in particular, we call lambda greater than or equal to 0 the Novikov ring. And a compact symplectic manifold K omega is said to have contact type boundary if there exists a Liouville vector field X defined on a neighborhood of the boundary of K. And the definition of the Liouville vector field is that the Lie derivative of omega with respect to X is omega itself. And one nice thing about contact type boundary is that it has a contact structure, and the contact form is given by the restriction of the interior multiplication of omega by the Liouville vector field X to the boundary of K. And the symplectic completion K hat of K is the symplectic manifold given by the gluing of K and the boundary of K times the positive real line. And they are glued along the flow of the Liouville vector field X. And this is also a symplectic manifold. Okay, to define the S1-Equivariant relative symplectic cohomology, the first thing that we need to do is to specify which Hamiltonian functions that we are going to use. And here is the definition. Let M omega be a closed symplectic manifold and K be a compact domain with contact type boundary. Then a contact type K admissible Hamiltonian function is a smooth function on S1 cross M, satisfying the following conditions. First, H is negative and C too small on K. And since K has contact type boundary, we can consider it symplectic completion. But of course, all of the symplectic completion cannot be embedded inside of M, but we can at least consider the small neighborhood of the boundary. So I will call that the neck. So in the first third of the neck, this Hamiltonian function is just convex and increasing function, and it only depends on rho, which is the coordinate on the positive real line. And the second third of the neck, it's a linear function with some restriction on its slope. And the restriction on its slope is that it is not a period of any periodic Reeb orbit on boundary of K. And on the last third of the neck, this Hamiltonian function is concave and increasing, and it only depends on rho as well. And outside of the union of K and the neck, it's C2 close to a constant function. And we denote the set of all contact type K admissible Hamiltonian functions by HK contact. And here is the function that I have in mind. So on K, this is small and negative, and convex, linear, concave, and C2 close to a constant function. And I will call Hamiltonian functions coming from this lower part, lower orbit, and those coming from this bigger part, upper orbit. And the S1-Equivariant floor complex of H is defined to be the tensor product of the polynomial ring over the Novikov ring with the usual floor complex. And here U is a formal variable of degree 2. So U to the K in this complex basically stand for a critical point of a perfect Morse function on CP infinity, the classifying space of S1. And the S1 equivariant Floer differential of this Floer complex has the following form. And the recipe for this differential is basically given by Bourgeois and Wansha. So let's choose a cofinal sequence Hn in HK contact, which means this is increasing sequence of functions, and the limit of Hn Tx is 0 if x is inside of K, and this limit is infinity if x is outside of K. So we are now ready to define what we want, but one might attempt to define the S1 equivariant relative symplectic cohomology as follows. So we have a cofinal sequence here, and we can consider their Floer complex. And we also have continuation maps between them. We can take its direct limit and then take cohomology. But this definition is not correct because it does not depend on K. So we need one more ingredient. And the clever idea of Varolgunes is that we complete the complex. So what's the completion? I will explain what it is. Let's say A is a module over the Novikov ring. Then the completion, A hat of A is, okay, so we have A here, and we can tensor it with Novikov ring mod up by lambda greater than or equal to R. And these form an inverse system. So we can take its inverse limit. And that inverse limit is the definition of the completion. And with this in mind, we can have the correct definition. So we choose a cofinal sequence in HK contact and consider the S1 equivariant Floer complex of them and take the direct limit, and we need to complete it. And once we complete the complex, we can just take cohomology function to get what we want. Then what is the purpose of completing the complex? Usually, by completing the complex, we can ignore the upper orbit. Completion process can kill the upper orbit. So this makes things different. And one quick question that you have in mind, you might have in mind is that, does it really depend on K? And the answer is yes, because of the nice example due to Varolgunes. So let's say S2 omega is the two-dimensional sphere equipped with an area form omega, and the total area of S2 is assumed to be 1. And let D delta be a smooth disk of area delta inside of S2. Then usual S1 equivariant relative symplectic cohomology is always 0, regardless of the size of D delta. But the relative version of it does depend on K because it is 0 if the area of the disk is less than 1/2, and it is a direct sum of two polynomial ring over Novikov field if the area of the disk is greater than or equal to 1/2. So it does really depend on K. And one nice feature of relative symplectic cohomology introduced by Varolgunes is that it can detect the displaceability of a subset. So let's let M omega be a closed symplectic manifold and K be a compact subset. And if K is displaceable, then its relative symplectic cohomology vanishes. And we can obtain a similar statement for the S1 equivariant version of it. To have the statement, we need the following theorem. M and K are as above. Then we have a spectral sequence which converges to the S1 equivariant relative symplectic cohomology of K inside of M. And the second page of this spectral sequence is given by the tensor product of the singular cohomology of the classifying space of S1 with the relative symplectic cohomology of K inside M. And with this in mind, we can actually have similar result for the S1 equivariant version. So let's say K is displaceable, then by the result of the Varolgunes, its relative symplectic cohomology vanishes. which means the second page of this spectral sequence is 0, but this spectral sequence converges to the S1-Equivariant relative symplectic cohomology, and this should be 0. Okay, now I will explain relative symplectic capacity, but we need some assumptions. Here are some list of our assumptions. So from this point on, we assume that M omega is symplectically spherical, which means the symplectic form omega and the first Chern class of the tangent bundle of M vanish on each spherical classes. And we say that the boundary of K is index bounded if for each integer L, the set of all periods of constructible rib orbits of boundary of K of Conley-Zander index L is bounded. So we add this index boundedness condition to our assumption list. And this assumption is actually a way to assert that we can actually ignore the upper orbit. And we can consider its action filtration. So this is generated by Hamiltonian orbits with action greater than L. And we can also consider the negative S1-Equivariant relative symplectic cohomology, and this is generated by non-constant Hamiltonian orbits. And we can also consider its action filtration. And here is the definition of a relative symplectic capacity. Let M omega be a symplectic manifold and K be a subset of M. Then a relative symplectic capacity C assigns to each triple mk omega a number C mk omega, and it satisfies the following two conditions. First, monotonicity. If there exists a symplectic embedding from M omega into M prime omega prime, such that the interior of the image of K lies inside K prime, then the relative symplectic capacity of mk omega is less than or equal to the relative symplectic capacity of M prime K prime omega prime. And the second condition is conformality. So if R is any positive real number, then the relative symplectic capacity of mkr omega is R times the relative symplectic capacity of mk omega. And we will usually drop the symplectic form from this notation if everything is clear. Here is one short history about symplectic capacity. Floer, Hofer, Wysocki introduced the symplectic homology capacity, which I will usually denote by CSH, using symplectic cohomology. And Gutt and Hutchings introduced the Gutt-Hutchings capacity, denoted by CKGH. So this is a sequence of symplectic capacities. And the main ingredient to construct this capacity is S1-Equivariant symplectic cohomology. But now we have relative symplectic cohomology and S1-Equivariant relative symplectic cohomology. So the question is, can we define a relative version of symplectic homology capacity and Gutt-Hutchings capacity? And the answer is affirmative. We can construct a relative Gutt-Hutchings capacity and a relative symplectic homology capacity. And here is the definition of the relative symplectic homology capacity. To define it, we need the following exact triangle combining this singular relative cohomology and relative cohomology and negative relative cohomology. And we label the horizontal map by JL. Then the relative symplectic homology capacity of K inside of M is defined to be the supremum of L, such that JL of 1K vanishes. Here 1K is the unit element of this singular cohomology. And we need minus n in front of it because of the sign convention that we are following now. And I will not give you the definition of every Gutt-Hutchings capacity, but I can at least give you the definition of the first one because it is our main interest. And define the first relative Gutt-Hutchings capacity, we need the S1-Equivariant version of the previous exact triangle. And similarly, we label the horizontal map by JS1L. And the first relative Gutt-Hutchings capacity is defined in an analogous way. As you can see on the slide. Here is one more history about symplectic capacity. Gutt and Ramos proved that the kth Gutt-Hutchings capacity is equal to kth Ecklenhofer capacity on every star-shaped domain inside of the Euclidean space. And Abondandolo and Kang proved that symplectic homology capacity coincide with the first Ecklenhofer capacity on every convex domain inside of Euclidean space. So the question that I had was this one. Is the relative first Gutt-Hutchings capacity equal to the relative symplectic homology capacity? And the only answer that I have at the moment is sometimes. So generally, the relative first relative Gutt-Hutchings capacity is less than or equal to the relative symplectic homology capacity. And to prove the other inequality, we need some type of convexity assumption, which is the following. So let sigma psi alpha be a contact manifold of dimension 2n-1, where psi is contact structure and alpha is contact form. We assume that the first Chern class vanishes. Then this contact form alpha is called dynamically convex if every contractible periodic ring orbit gamma of alpha has Conley-Zander index greater than or equal to n+1. And under this assumption, we can actually prove the other inequality, which implies that the first relative Gutt-Hutchings capacity is equal to the relative symplectic homology capacity. And here is one more thing that I want to say. We already saw that relative symplectic cohomology introduced by Varolgunes and S1-Equivariant relative symplectic cohomology can read the displaceability of a subset. And the question that I had was, can relative symplectic capacity also detect the displaceability? And the following theorem is one result in that direction. So if symplectic homology capacity of K inside of M is infinity, then K is a heavy set, and hence it is not displaceable. Here, the notion of heaviness is some type of symplectic rigidity introduced by Antov and Poltorovich. And that is all I want to share for today. Thank you for listening.
Any questions?
I have a question. Can you hear me?
Yes.
Thank you for a very interesting talk. I was wondering if your capacities have some kind of spectrality property, like is your relative capacity equal to the period of some Hamiltonian array orbit or something like that?
At the moment, I'm not sure that's the thing that I want to study, but I can have, I think I can have some comparison of this relative symplectic capacity with other, like such as what relative Hofer-Zander. I can make a comparison of them, I guess.
Thanks.
Okay, so it's slightly related. Maybe the Gutt-Hutchings capacity can be calculated for the toric domains. So it can be read from the moment map. Is there any equivalent here to the relative version?
Equivalent version of a relative Gutt-Hutchings capacity?
Yeah. So can you read it easily for toric domains, some convex or concave toric domain?
Not sure, sorry.
Right.
I think there is an alternative way to compute relative Gutt-Hutchings, because in this slide, M was assumed to be closed, but it can be extended to like symplectic completion of the Liouville domain. So I think we can get the similar result due to like Hutchings and Gutt. Does it make sense?
No, I'm not sure I understand.
One second. So in this notation, M is assumed to be a closed symplectic manifold, but it can be actually extended because M can be replaced. If K is Liouville domain, then M can be like the symplectic completion of K hat.
Mhm.
And this is actually the usual Gutt-Hutchings and usual symplectic homology capacity. So in that case, we can have the alternative way of describing it.
Okay, thanks.
So currently it's only for spherical, you said. So what about?
At the moment, yes.
So you're working on extending this to let's say monotone.
I mean, the problem is that at the moment, I don't know how to slice out the critical points, because if we have an action functional, critical points can be sliced out as a subcomplex. But if we don't have like well-defined action function, I don't know how to cut it out from the complex.
Okay, thanks.
Okay, so let's thank you again.